So this chapter is on how the climate changes we looked at starting from MIS 6 into the Holocene or even the Anthropocene, and how it is manifested in global landscape. Obviously, landscape changes, vegetation changes, desertification, rainfall, water resources, food, etc. must have affected the human migrations, speciations, settlements, behavioral changes, conflicts, and so on along the way. But here there is a reliance on a model, which is a simplified Earth system model that we talked about before, the University of Victoria model. And it has several components, and it produces vegetation changes associated with climate changes and so on. What I want to do is then start with recapping the times of the climate change through the 135,000 years just briefly, and look at feedbacks, because we mentioned feedbacks before. One of the tricky things is when a model is so coarse resolution and doesn't have things like land ice, and there are uncertainties in models' representation of the carbon cycle, the vegetation dynamics, aerosols, and so on. Many feedbacks may be missing. So what is done is typically validate the model against data from pollen data, loess data, ice core data, lake sediments, whatever proxies we have talked about will all be used to convince ourselves that the model is doing a reasonable representation of some climatological conditions and some variability and so on. But that hardly guarantees that everything is totally very robust and accurate. So we have to keep that in mind as we look at the effect of 135,000 years of changing climate on the landscape, starting with this figure, which just recaps our main time scale, 140,000 years, the middle Pleistocene into the late Pleistocene, remembering that the Pleistocene starts around 1.8 million years ago with the 100,000 year transition happening about 1 million years ago. And here we are in the Holocene, and we separated now this into the Anthropocene as well, which is not always shown in most of these studies, as we already discussed. So benthic delta O18 per mil, which is obviously a measure of cold and warm temperatures, and you can easily orient yourself because Holocene is warm. So when there is glaciation, delta O18 is left behind in the ocean because more of the O16 gets locked up in the glaciers, so it gets enriched in delta O18. So these are colder times. So we are starting with a cold time, and we have had many glaciations, deglaciations, stadials, interstadials, Dansgaard-Oeschger events, Heinrich events, everything we talked about before. And the marine isotope stages, which are counted based on the oxygen isotope signature, are split into 5, but 5 has A, B, C, D, E that the book goes through for details of climate change and vegetation changes. 4 through 1, so here we are through the end of the last ice age, deglaciation into the current interglacial. We can look at this in many ways. So this is looking at the Greenland signature, which is zoomed into just the 80,000 years ago to look at more clearly the modern warm interval as seen in the O18 deficit, or in the ice core. So you have to remember benthic versus ice core data. Delta O18 signature goes the other way. So here we are again colder, but now more depleted in O18. Warmer has less depletion, which is obviously different than what we were looking at here in the positive scale. Okay. So we had Dansker-Rushker events which occur at about 1470 year time scale, and then Heinrich events which are lower frequencies. So the sea level along the way has also varied, as you can imagine, but one thing to remember is that of course larger continental ice sheets lock up the water on land, so sea level drops. So relative to today it would be minus 120 meters at the peak of the last glacial, so last glacial maximum around 21,000 years ago. But this is estimate of the global mean. Regional sea levels matter a lot, obviously, just as regional climates and regional vegetations matter a lot. This is from a nice paper by Karen Kofeld, which looks at the ocean part of the changes, especially in terms of carbon uptake, because during glacial deglacial cycles we know that CO2 is a positive feedback, so is methane. As it gets colder and glaciers build, CO2 drops, which favors further cooling, and when deglaciation happens, CO2 increases and further favors faster warming. So there are the orbital forcings shown. You can see which cycle is which by looking at the frequencies, obviously, but we are looking at obliquity and precession, and we are looking at again marine isotope stage 6 through 1, and relative sea level that we already looked at. CO2, just to remind ourselves that when deglaciation happens and sea level rises, we're going from minus to 0 current levels here. So CO2 increases, so we go about 200 to 280 ppm, which was the pre-industrial level, and this would have had feedbacks. There are two questions. One, what determines this change from glacial to deglacial? There are multiple hypotheses, one being that during cold times dust is higher, so maybe iron fertilization of the ocean happens and more CO2 uptake happens, which could explain lower CO2. But shelf areas change, phosphorus supply, photosynthesis can also change, coral hypothesis. So there are many ideas, which again means that no single hypothesis explains the 100 ppm or so change that occurs. This is the Antarctic sea level, which obviously corresponds to generally the global signature that we've been talking about. But focusing on the CO2 and CH4 changes again, this is from the Vostok Ice Core, similar time scales, reminding ourselves that temperature leads in the orbital forcing time scale, CO2 and methane follow. So here is the deglaciation and increase in CO2 and methane, slow glaciation, slow drop in slow cooling, slow drop in CO2 and methane, and so on. This is from the Penn State John Dalton's course that I stole from. What happens in the ocean? It's important to understand because ocean feedbacks would affect the coupled climate rainfall distribution, ITCZ, and hence vegetation and human migrations and so on as well. So if you look at the inception of the glacier 105 to 115,000 years ago, without using the corresponding marine isotope stage numbers, the surface response would be that there is polar cooling in both places, which would affect the deep water formation and the bottom water formation, which would affect the cells that we talked about before. So there is buoyancy loss at high latitudes with certain coverage in the southern hemisphere of shelf ice, sea ice, and so on. And there is a mild surface cooling when inception happens, which favors, of course, continued cooling. So you can see where we are in terms of the inception of the slow cooling. Whereas in the mid-glacial 59 to 68,000 years ago, the deep ocean response is imagined this way, where you have more exposed ocean. Remember, the atmosphere gets cold very quickly, has low heat content. How much heat it can take up from the ocean depends on sea ice coverage and so on. So there is maximum cooling here and maximum cooling here, and you have increased dust loading. So iron serves as a nutrient that favors increased photosynthesis phytoplankton blooms. I'm being a little too quick there. There are certain places like the Eastern Pacific around Galapagos and the Southern Ocean where there is plenty of nutrients like nitrate available, but they are not being consumed because critical micronutrients like iron, which are needed for effective photosynthesis, are not available. So those are called high nitrate, low chlorophyll regions because available nitrate is not used up because of this deficient iron supply. So during cold conditions, it's drier overall, reduced rainfall because of cooling. So there is near max surface cooling here, for example, and that leads to more dusty environment, and dust carries iron, and that is expected to enhance phytoplankton production and drawdown of CO2 into the ocean. So you can see the changes here, maximum cooling, so you have seriously moved the deep water formation site and you have changed the circulation here. So warmer waters here than here, and here is where we are already deep into the mid-glacial period. Okay, so this is basically highlighting the ocean's role in the feedbacks. Okay, I think I'll stop this here and then come back and add a little bit more about the model and the kinds of things the model has to worry about, and I will use the dust feedback relating to this process again from another paper which argues that dust was an important player. As we already talked about a little bit, dust is aerosols. In the modern climate, we worry a lot about it because it has the direct impact of radiative forcing by affecting how much sunlight can reach the surface. For example, it can create what is called solar dimming, so prevent the land from warming much because of the pollution and the aerosols and the dust. It can also affect indirectly the cloud microphysics, cloud condensation, nuclei, droplet sizes, total amount of rain. Instead of heavy rain, you would get drizzle. It's also argued to affect cyclones and of course chlorophyll production and ocean heating and so on and so forth. So we'll talk about those. I'm doing this before getting into the model simulations because you need to keep these in mind when you look at model simulations, even though the model simulations are validated to make the arguments that are made about dynamic changes and vegetation changes, climate change, vegetation change, and putative impacts on hominin migrations, diaspora, speciation, and so on. Okay, so let's leave this podcast here.